This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about statics homework problems 655, 59, and 60. These are all simple machines, and the key is breaking them into parts and doing free body diagrams of each part. And with a systematic approach, you can solve these problems. The first one was a clamp. This clamp is clamping these two boards together, and they're pressing together with a force of 100 pounds. The find was to find the magnitude of the force that pin D exerts on member CDE. And the first thing to note, as we said, is to try to find two force members. We can see that screw, shown in green there, is a two-force member. Forces exerted at B and C have to be 2 points, so they have to be in a line, collinear. So we do a free body diagram of member ABD. We sum moments about D, which is 0. The only thing we have there is the 100-pound force at 4 inches, and creating clockwise rotation about point D, and then also creating clockwise rotation about point D is the force in BC with a 2.5-inch moment arm. We solve for that. We get that the force in BC is negative 167 pounds, so we reverse the sign of that, and we reverse the sign of this, so we make it point to the marker isn't very good. So FBC must be in compression. So we can reverse the sign of that and make it in compression on point B. Similarly, we can now do sum of forces in the Y to get the dy force is equal to 100 pounds negative. So we reverse the sign of that one. It is down on the pin, or down on the member CDE. And sum of forces in the X direction, all we have is this now negative 167 from FBC because it's in compression to the left, plus dx. We get that dx is equal to positive in this same direction we assumed it, to the right, 167 pounds. The resultant is the square root of the sum of the squares, or 194 pounds. So you see the key is to break it into parts and analyze those parts. 659, I'll just give you a couple of hints to get you going. We have really a bolt cutter, and at the handles we're exerting a 90 Newton force. And this is the arm, this is the jaw, this piece in red pieces. There's a green link that connects them together. The bolt is shown in blue there, and the arms connect to the jaws right here back at this point. So we do a free body diagram of the jaws, a jaw, and we see that we have these forces coming from the arm, Fx and Fy from the arm. We have a force in the link, which is a two-force member, and so it's got to be in that line. Plus we have the force in the bolt. It's exerted on the bolt, and that's what we want to know. We can do a sum moments about the link to get the force on the bolt relationship as a function of the force on the arms, on the arm. Then we can do a free body of the arm, put the 90 Newton force out here, the force reaction from one arm to the other at point A, AX and AY, and then we have the force in the arm that we got from up here, which we just have a relationship between the Y force in the arm and the force on the bolt. We can sum moments about point A, and that gives us the force in the arm, which is 486 newtons. That's a partial hint, partial solution. From that, in this relationship, you can get the force on the bolt. And back to this one, back to the free body of the arm, you can do sum of forces in the Y to get the force AY. AX is equal to 0 because there is no other X component putting any force in the X direction on this arm. Final question is number 660, ice tongs, which you hold in the middle. Unless you've seen one, it's kind of hard to visualize, but you hold that cable in the middle, and that pulls up on these two bars, AB and BC, and then they squeeze the ice, the block of ice, which is a mass of 50 kilograms. Convert that to newtons. It's 490.5 newtons. So we do a free body diagram of joint B to get the force in the cable, which has got to be equal to the weight of the block of ice, 490 newtons. From that, the geometry of these two force members, we have to note that AB and BC are two force members. From that we can compute AB, the force in AB and the force in BC, and they are equal 306 newtons, and they are in compression. So I need to reverse the sign of those, obviously. So they're really going like that. Then I do a free body diagram of the member ADF, which is one half of it. I reverse my direction of FAB. It's compression on that joint B, so it's got to be compression at the other end too, at point A. I can sum moments about point F to get the force in the horizontal member DE, which is also a two force member. And then I can sum forces X and Y to get the forces at F, although the problem doesn't even ask for it. It's kind of a check to see the force in Y is equal to half the weight of the block. So it's pretty simple if you just break it up into parts and pieces. Go for it.